Welcome to CS 712. This session is on regular languages and regular sets, and it should be a review for most of you. What do we mean by a language? A language is just a set of strings. Where the individual elements that make up a string are chosen from a finite set called the alphabet. So for example, here's an alphabet containing two symbols, A and B, and here's a couple example languages built on that alphabet. This one is the finite set of just the string A followed by the string B. Not followed by, it's a set containing two elements, the string A and the string B. And it's a finite set, so it's not that terribly interesting. Let's look at an infinite set here. Here's an infinite set defined on the alphabet AB, which is a string of n A's followed by a string of n B's. So again, we're defining a set of strings defined over this alphabet, and such a thing is called a language. If A is an alphabet, then A star is the set of all strings over A. And any language over A is a subset of A star. Note that the empty string is a string. And the empty string is hard to see, so we'll use a special symbol for it. We'll use lambda for it. Also note that the set containing the set containing lambda is a language. Okay, so since lambda is a string, right, the set containing just that string is a language. Okay. Also note that the empty set is a language, denoted, of course, with the empty set symbol. We're going to talk about concatenation of strings. So I can concatenate two strings here. And again, I'm parenthesizing the strings because the convention is that concatenation, there is no operator. It's implied by placing the two strings next to each other. So I'm just parenthesizing them to emphasize where the strings end and begin, and then there's this invisible concatenation operator in the middle. So we concatenate AAB with BA, and of course the result is AAB, BA. Well, we can then talk about the product of languages. So if we have two languages, L and M, I can talk about L times M, which is defined as the set of a set of strings where each string is built from concatenating a string from the first set with a string from the second set. Okay. Again, this is string concatenation here. And we could think about the product of a language with itself, starting off with, if I concatenate 0 times, then the result is simply the set containing the empty string. Okay. There's nothing to concatenate in essence, so I end up with just an empty string. Okay. Or I can talk about concatenation being done n times, where it's just a string chosen from the language L concatenated with n-1 other strings chosen from the language L. Okay. That allows us to define this L star then more precisely, right? It's the sort of an infinite number of unions where we start out with L0, union with L1, union with L2, and so on. Okay? And we'll often refer to that as the closure of L. Okay. A couple notes now. If we take the language consisting of the empty string and we form the closure of that, well, we don't get anywhere because we just keep concatenating lambda with lambda, which results in lambda Um, so lambda star produces lambda. Again, I should be more careful. The set containing lambda star produces just the set containing lambda. Okay. What about the empty set? What if we form the closure of the empty set? Well, we're taking, an element of the empty set concatenated 0 times. Well, that's just the set containing the empty string. Okay. But if we can try to concatenate nothing with nothing, we don't get anything. We just get the empty set and the empty set. So because of the way this 0, this 0 product is defined, we end up with just lambda here, the set containing lambda, as the result of empty set star. Okay. Let's look at a few other things. What if we concatenate the set containing lambda with another language, L? Well, it's whenever I concatenate lambda with anything from L, I'm just going to get back the same string in L. So the product of those two languages is simply L. Likewise, when we reverse them, it's going to be the same idea. What about if we concatenate, if we take the product of the empty set language with any other language? Well, again, there's nothing here to concatenate, so we end up with nothing. Same thing when we reverse the operands. Okay. And of course, if you take the empty set union a language, well, that's just the language also. Okay. Well, why are we interested in languages? It's because we're interested in parsing. And parsing in the theoretical realm is often called the recognition problem. So we want to know if the string S is in a particular language L. If you think about that, that's what parsing is. Right? We want to know, is the program a legal program with respect to a particular language? Okay. So we're going to be looking at mechanisms for solving the recognition problem. And let's start by looking at a particular subset of languages called the regular languages. Again, let's assume A is our alphabet, which is a finite set of symbols. And we can talk about a regular language. And the notion of regular language and regular sets, which is I've written down here at the bottom. A regular set is just a notation for describing a regular language. So I'm going to set them up in parallel on this slide. And the definitions are recursive. There's a base case. Okay. The empty set over here, the empty set is defined to be a regular language. The set containing the empty string is also a regular language. And then the other building blocks is that every singleton set containing one symbol from the alphabet is also a regular language. Okay. And we denote those sets in a straightforward way over here. We'll talk about this regular language, the empty set. We'll talk about it with this regular set. Okay. And this set containing the empty string, we'll denote it with just lambda over here. And then the regular language containing the singleton string A is denoted by A over here. Okay. Where again, A is an element of the alphabet. So that's our base case. And then we have some operators that allow us to generate more regular languages from the base. Okay. So again, if L and M are regular languages, then the following are regular languages. The union. Okay. The union of the two languages is also regular. The product of the two languages is also regular. And then the closure of one of the languages is also regular. And in fact, M star would also be regular here, right? Any regular language, if you apply the the asterisk to it, it's also regular. On the corresponding side, I'm going to add parentheses to my regular set notation now. Just allow me to parenthesize things because I'm not going to talk about the precedence of these operators. So a regular set, if R is a regular set, then the parenthesized notation, putting parentheses around that regular set is also a regular set. Now the rest of these will match up across the two columns, right? Union is denoted by the OR bar here. Okay, so if R is regular and S is regular, then the alternation, the alternative of taking either an element of R or an element of S is also regular. And if you think about that, that's going to be like union, right? Right, I either match something from R or I match something from S. That means the set that's being recognized is really the union of what R denotes and the union of what S denotes. Likewise, we have a product operator here, and again, I will, it's hard to see. It's that invisible operator in there separating R and S, but you take something that matches R and you concatenate something that matches S, that's also a regular set. And finally, the Kleene star, we refer to this as, which means 0 or more repetitions, corresponds to the closure of a regular language. So again, regular set is just a notation for writing down a regular language in a sort of compressed form. And again, I think all of you have worked with regular sets using various tools over the years, like grep, for instance. Notice that from a theoretical point of view, there's just these three operators. There's just alternation, concatenation, and Kleene star, 0 or more. So a lot of the terminology, a lot of the notation, extended notation that you see in real tools, like plus for one or more, they can all be expressed in terms of these three operators. Or the question mark for optional can all be expressed. Those are just extra syntactic sugar to make it maybe a little easier to express regular sets, but they're not required from a theory point of view. All right, let's look at an example of a regular set. So, got an alphabet, again, just the two symbols A and B. And I've written down a regular set here. Again, I'm using the parentheses just to group things and make it clear what the order is. So in this case, concatenation happens before the alternation. Okay, concatenation happens before the alternation. The alternation happens before the star. Okay, so I'm choosing A concatenated with B or B concatenated with A. And then I'm repeating that 0 or more times. Because it's 0 or more, I have in my regular language, I have the empty string, because I could choose to do 0 repetitions. Then I have AB, or I have BA. Then I can go around the circle a couple times, ABAB, or ABBA, or BAAB, BABA, and so forth. Again, this is going to be an infinite set. Okay, so I'm hoping that reminds you a little bit about, formally about what we think of as languages and introduces you to regular languages and regular sets. Let's stop here.